And esters. All right, so remove the acidic proton, you put an alkane chain on the carboxylic oxygen. So esters are to carboxylic acids what ethers are to alcohols. So up here you have ethanol, you pop an alkane chain on there, you have ethoxypropane. Down at the bottom, you have acetic acid and propanol. You do a dehydration synthesis, and what you get is propyl acetate. Okay. So there's, first off, you'll notice there's a little bit less flexibility in terms of naming. We'll get to that. Now, esters are vital to biology in a way that ethers are not. Esters are kind of all over the place. I've already mentioned one of them, fat. A fat molecule is a glycerol backbone plus 3 fatty acids in a triester. You see, you got 3 ester bonds there in between the glycerol backbone and the 3 fatty acids. They're also responsible for the aroma of a lot of different fruits, apples, pears, bananas, and so on. Those are esters. They have an aroma just like carboxylic acids do. But they don't necessarily smell like sweaty feet, unless you're talking about the durian, which is a fruit from Asia known for being smelly. It's considered a delicacy because rich people will eat any damn thing if it's from far away. They're more polar than alkanes, of course. They have those carbon-oxygen bonds in there. They're more reactive than alkanes. There are a number of significant reactions involved with esters. But they're not acidic, of course. They've lost the acidic proton that the carboxylic acid used to have. Now, let's go ahead and talk about naming just a little bit. Like I said, they are less flexible than ethers. For ether, the more important chain is the one that gets the name. The other one becomes a side chain. Not so for esters. The one with the carboxylic acid group, the carbonyl carbon, in other words, gets the priority. And the other chain, no matter how complicated it might be, is going to be your side chain. Okay. So for this example, despite the fact that it's a lot more complicated, and you'll see I actually had to take a moment to work it out, this one, that complicated side chain, is just a side chain. It does not get any sort of priority. The other one gets priority, and it's just a simple hexanoate. Okay, you sort of treat this like an ionic compound. So if you mix, say, sodium hydroxide and acetic acid, the result will be, a neutral solution, right? Well, slightly basic, a weak base of sodium acetate. So you treat the side chain as sort of like the ion, the sodium in that case. So it's, this blah, 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 enyl hexanoate. Okay. And to that end, I want you to notice there's a space in between the side chain and the hexanoate. This is one of the rare occasions when an organic molecule has a space in the middle of its name. Now, in terms of some of their other activities, esters, I want to go ahead and take advantage of them to highlight the fact that alkane chains are not negligible. They do have an effect on the way that a molecule will behave. I mean, we've been focusing on the functional groups because they can alter the behavior drastically, but they're not, nothing. So a fat, for example, is not water-soluble. It's a triester. Each of those esters is a significant region of polarity. So they should make the fat molecule more water-soluble. The problem is that the fat molecule also has those really long fatty acid tails. I mean, those are, 16, 18, 24 carbons long. They're huge, relatively speaking, and, they sort of flippity-flop around, and they hide those ester bonds, those ester groups, from the water that they might want to interact with. So fat is not water-soluble. Whereas if you break those ester bonds, if you dissolve your fat in a strong base, sodium hydroxide, what you'll get is a fatty acid or its conjugate base. And all of a sudden, that carboxylic group is no longer hidden. So fatty acids are water soluble. In fact, they're soap. So I just want to take advantage of that to emphasize that these the alkane chains are not having no effect. They can be fairly important. But in any event, esters, they're polar, they're reactive, they're non-acidic. They're not acidic. Those are some of the chemistry things to take away from esters. And finally, last but not least, well, kind of least, we have the amides. That's where you remove the hydroxy group from a carboxylic acid and replace it with an amino group. So, for example, here we have acetamide. Yeah, that's another common name. It should be ethanamide or ethanamide, but what you gonna do? And then down below it, we have butanamide or butanamide. I've never really heard any sort of consistency when it comes to how to pronounce these, butanamide versus butanamide. Maybe if chemists didn't come from all over the world speaking in all the tongues of men, then yeah, there might be some consistency, but there really isn't. So just, go nuts. Have fun with it. Amides are kind of super important in biology and biochemistry and organic chemistry. Among other things, not only do they show up in plastics and organic synthesis, but they are kind of important to life. Here we have an example of just that. An amide, or an amine, will react with a carboxylic acid to produce an amide. And in this case, the carboxylic acid and the amine we're reacting are amino acids, producing an amide that is a dipeptide. And the amide bond is known as the peptide bond. It's a dehydration synthesis. So amides can be kind of super duper vital. Now, when it comes to their properties, they are less basic than amines. Because here we have a sort of very simple amide, and I've drawn it with the non-bonding pair of electrons, because what can happen is the non-bonding pair can sort of hop down into the carbon-nitrogen bond, forcing the carbon-oxygen bond, the carbonyl bond, to become a single bond. And so what you get is this resonance structure, where you have a double bond between the carbon and the nitrogen, and a single bond between the carbon and the oxygen, and the nitrogen and the oxygen exist as ions. These two resonance structures don't exist equally. They're not like, the resonance structures of carbonate or something like that. Instead, the amide is about 2/3 the neutral structure up top, and 1/3 the double ion down bottom. Nevertheless, this means that they're not very basic, because that structure down bottom is no longer able to donate a pair of electrons. So it's no longer a base. It doesn't have electrons to give. The structure up top does, so it is somewhat a base. But that resonance structure means that it's not as basic as it could be. As for solubility, amides are about as soluble as esters. They are less soluble than equivalent carboxylic acids and amines, though. There's just more stuff there taking up room. So they're not as soluble as they might otherwise be, as you might expect them to be. Now, when it comes to naming, they are sort of in between carboxylic acids and amine and other things. They're a little bit simpler than carboxylic acids, the carboxylic acids. they're a little bit more complicated than most other stuff. Up top, we have an amide with an amino side chain, and that's just 4-amino-pentanamide. But down bottom, it's lost priority. So instead of being an amide, it is a carbamoyl side chain. And you'll notice that instead of being pentane, there's 5 carbons there, but now it's 4-carbamoyl butanamide. The reason it's simpler is because you no longer have to, you don't treat it like an ester. Okay? So if you have side chains, like we do here, coming off of the nitrogen, then you can just treat it like you would chains coming off of an amino group. So this is N,N-dimethylbutanamide. You no longer, you don't have to worry about, methylbutanamoate or anything like that. No. This isn't like an ester. You just treat it like an amine in this case. But the fact that it is acting like a carboxylic acid in terms of if it loses priority is what makes the carbamoyl kind of annoying. So here we have 3-carbamoyl propanoic acid. That 4th carbon it's considered no longer part of the main chain because it's instead part of the carbamoyl group. So it's just something you have to keep in mind. Sort of like an amino group, the nitrogen isn't part of the main chain. A hydroxide group, the oxygen isn't part of the main chain. You just have to get used to thinking that sometimes carbons can be part of the main chain, and sometimes they can be sort of stolen away and made into a group over on the side. Finally, because we have this nitrogen with its ability to branch off multiple times, amides can be primary, secondary, and tertiary, just like aminos can be. So a primary amide is just bound to the the carbonyl carbon. A secondary amide is bound to the carbonyl carbon and another alkane chain. So it's bound to 2 carbons, secondary, 2 carbons. And then we have the tertiary amide that has a total of 3 carbons bound to the nitrogen. The carbonyl carbon and 2 others. All right, so that's really all I really want you to know about amides. So let's go ahead and finish up here. Just to take a brief glance back at the priority list. And here, one last time, is our list of priority from highest to lowest. Up at the top of the list, we have carboxylic acids, then esters, then amides and aldehydes and ketones and hydroxides and amines. These are all the suffix groups that I've asked you to learn about. Everything else we've covered is not a suffix group. And that does it for Chapter 20, and that does it for these videos, and that does it for listening to my stupid grading voice. This has been, it's been a journey, it's been a ride, a roller coaster of emotions. I will see you in class, perhaps, some Egyptians believe.